The correct answer for this question is D only, the standard error of the mean. This is because when we have 246 patients, that is quite a lot of patients. The central limit theorem would have started kicking in already. So we would have the mean, the median, and the standard deviation for the sample to be quite close to the mean, the median, and the standard deviation for the total population. We wouldn't expect those parameters to change very much if we added another 100 people. But the standard error of the mean, which decreases directly with the number of samples that we have in our sample size, would definitely go down if we added 100 people to the number of patients that we have. In this case, because we have a very small sample size of only 13, we need to opt for a t-distribution as opposed to the normal distribution. A t-distribution has one less degrees of freedom than the number of the population of the sample. In this case, because we have 13 children in the sample, the degrees of freedom turn out to be 12. The formula for the standard error is given by standard deviation divided by the square root of the number of observations in the sample. And if we substitute the values that we have, this comes out to 0.23, which tells us that A is the right answer. For this question, we know that the mean is 0.66. How do we know this? This is because we have 20 patients out of 30 who improve based on the exercise stress test. We also know that the standard error is given by the formula P times 1 minus P by N. In this case, our P is 0.66, 1 minus P is 0.33, and N is 30. So we have a standard error of 0.086. The confidence interval is now given by the mean, which is 0.66, plus or minus a z-score corresponding to a 95% confidence interval, which is 1.96, multiplied by the value of the standard error that we just calculated. And this turns out to be 50 to 84%. Let's use the formula that we have for the odds ratio to calculate it using the values that we have in the 2x2 table. This comes out to be 10 by 40 divided by 5 by 55, which is an odds ratio of 2.75. B wants us to take the natural log of the odds ratio that we found, which is 2.75, which is 1.01. We know that the formula for the standard error of the log of the odd ratio is given by 10 plus 1 by 40 plus 1 by 5 plus 1 by 55. This turns out to be 0.586. The 95% confidence interval is now given by mu plus or minus 1.96 times the standard error. In this case, it's 1.01 plus minus 1.96 times 0.586, which is an odds ratio of minus 1.4 to 2.16. This question wants us to exponentiate the values we found in D so that we have the confidence interval in terms of odds ratio as opposed to log of odd ratio. So that would be an exponential of minus 1.4, which would be the lower bound, exponential of 2.16, which is an exponential of the upper bound. And in terms of the odd ratio, we get the confidence interval to be 0.87 to 8.66. The answer to F is false. The confidence intervals of the logs of an odd ratio are symmetric, as we just found, but when we exponentiate, the symmetry is lost and the confidence interval of the actual odd ratio is not symmetric. The answer to G is true. The 95% confidence interval for the odds ratio crosses 1, so we cannot reject the null hypothesis, and thus we know that P is greater than 0.05. Part A of this question wants us to roughly estimate the two-sided p-value associated with this distribution. If we count the number of observations that we have to the left of negative 25 and to the right of 25, we'll see that there are about 25 observations out of 1,000 that have these values and which are in the left or the right tail correspondingly. This translates to a two-sided p-value of 0.025. In this question, we know that the mean is 0, and x is 27, and that the standard deviation is 12.3. This means that the z-score is 2.2. This corresponds to a probability value of 0.014. Now, because we are looking at two-sided p-values and not one-sided p-values, we can multiply this by 2, and so the final probability comes out to 0.028. The next question asks us how the histogram would change if we ran the simulation for 10,000 times rather than 1,000 times. And the correct answer is 1, that it would simply be smoother, because as we have more and more observations, the central limit theorem will start kicking in, and we will have a more and more normal looking distribution. When we have 10 times more values, this distribution will look 10 times smoother. The correct answer to D is 2. The sample size of the hypothetical trial is larger, which is the reason that the p-value is lower. This question gives us the percentage of US adults who had 5 or more drinks in one day at least once in a given year, and we have trends for, let's see, we have trends for 7 years. We have the mean value as well as the 95% confidence intervals given. The question wants us to find for which years we could reject the null hypothesis that more than 20% of US adults had 5 or more drinks in one day at the 0.25 significance level. The answer is 2000 and 2003 only, because these are the only two confidence intervals which don't cross 20, and these are the only two confidence intervals for which we can safely reject the null hypothesis.